Let's do a different geometry of a capacitor and see how the equation for capacitance changes. It's still, caps are quite overvalued. That will never change. C will equal Q over delta V. In fact, again, that's how we're going to derive this. But you'll see that different variables matter in terms of what actually affects the capacitance. Again, it's all geometry materials. So far, we're just dealing with geometry. So here is a single sphere capacitor. I'm just going to draw it right here. Here it is. It's a sphere. It might be a Van de Graaff generator or a conducting sphere of any kind will work. And I'm going to say it's got radius r. And so we could charge it just like we charge a Van de Graaff generator with a bunch of positive charge or negative charge. I'm going to use positive charge for my example here. Okay. But you may say, JB, I only see one plate. There's only one place where there's charge stored. Where is the other plate of this capacitor? Well, when you have a single charged sphere, remember where we said that all these electric field lines end. Where do all those field lines end? The other plate of this capacitor is at infinity. There's negative charges out here at r equals infinity is where these negative charges are. So the other plate of this capacitor is at infinity. That's totally legal. The C kids will have to derive the capacitance of a nested spherical capacitor when you have a spherical shell around this thing that's a conductor also. But for right now, we're just going to figure out the capacitance of just this sphere with the other plate way out at infinity. So I'm going to just call this amount of charge on there Q. Q distributed evenly on that sphere. And to derive the equation for the capacitance of this particular capacitor, again, we have to just rely on the definition of capacitance. Caps are quite overvalued. So what is Q? Well, that's easy. I just labeled it Q. But what is delta V? Delta V, again, between what and what? Well, between this and the other plate, between this thing right here and the other plate, which is where? At infinity. So we're just asking what is the potential right there, and beauty of capacitors, I don't have to worry about sign, I don't have to worry about if this is higher or lower than infinity. In fact, it's higher potential. Positive charge would fall away from it to infinity. But all I got to do is put in the potential of this compared to infinity, which, as you recall, is K, the Coulomb constant. That's not a kappa, that's a K, Q over the radius of this sphere, capital R. Well, how simple is that? The Q's cancel, and you end up with just capacitance is the radius of this thing over the Coulomb constant, which we much prefer to write with these more fundamental constants. That would be epsilon naught again times 4 pi r. How easy is that? I probably should have mentioned the fact that this is r, the Coulomb constant is just 1 over 4 pi epsilon naught, and that's how I got this result. So the capacitance of this thing, again, only depends on geometry. We have not yet shown an example of how it depends on materials. But capacitance of a single sphere is epsilon naught times 4 pi r. If you triple the radius of this sphere, you have effectively tripled the capacitance, meaning for the same voltage, you could have triple the amount of charge on there just by tripling that radius. The capacitances for other geometries, such as cylindrical geometry, and as well as a nested sphere, in other words, a solid sphere inside of a spherical shell, those derivations of the capacitance are required for AP Physics C, and you'll have to do those yourself. Do not just look in the book and use those equations. If you do, you are shooting yourself in the foot for the AP Physics C exam. You are going to derive it every single time by using caps are quite overvalued. You start with that, and then you derive what it is for that particular geometry, which most often involves figuring out what the potential difference is, very often using calculus. Derive it yourself, because that's going to be the problem on my test and on the AP Physics exam, deriving the capacitance depending on the geometry.